Field lines are a visual representation of the direction and magnitude of an electric field. There are a few rules that field lines follow that help explain what information they portray and how they behave. The first is that field lines must begin on positive charges and end on negative charges. If there is no negative charge present, the field line continues to infinity. Though this might seem counterintuitive since electrons travel from negative to positive, field lines point in the direction that a second positive charge would travel. The second rule is that the number of field lines is proportional to the magnitude of the charge. So more field lines around a charge, the higher its magnitude. In the same vein, the strength of the field is proportional to the density of the field lines, so the closer together they are, the stronger the field. Hence, this field would be stronger than this one, even though they're both positive charges. Another rule to remember is that the direction of the field line is tangent to the field at any point. Basically, this just means that the field lines point in the direction of the electric field where they are in space. So, a point here will have an electric field that is headed in that direction, versus one here, the electric field would point in that direction. The last important rule to remember is that field lines can never cross. If they did, it would appear that the electric field would be going in two different directions tangent to those lines, which is not possible. So instead of crossing, they interact like vectors to show the correct direction of the field. For example, in this situation, these two lines would interact in a way that would create an electric field and an electric field line that is pointed in this direction. In addition to changing the direction of the field lines, this interaction makes it so that the field is weaker between like charges and stronger between opposite charges. As you can see here, there are more field lines there than there, because the field lines point away from positive charges and towards negative charges. Though the field is weaker between two like charges, far away from the charges, the field acts like there is one stronger charge. As long as you remember these 5 rules, you will be able to understand field lines and to know what they represent and how to interpret them. Say we have a point charge on an empty plane. This point charge creates an electric field, so I'll add some field lines according to the rules we just learned. If this were a positive field charge, the field lines would point away from the charge, but since it's negative, the arrows point in. Now I'm going to introduce a new concept, equipotential lines. As the name implies, equipotential lines represent where the electric potential is equal. Electric potential, or voltage, is an interesting concept. The electric potential of a test charge depends on both the strength of the point charge and the distance from it. This is represented by the equation V, or for voltage, equals K Q over R. K is a constant, and Q is the magnitude of the point charge, which is this, and R is the distance from the point charge. A change in voltage can also be found with the equation delta V equals negative E D, using the strength of the electric field and the distance traveled. Electric potential is not potential energy, but it shows us the potential for creating potential energy if a charge is placed at a certain point. Electric potential and electric potential energy are related by this equation. PE equals QV. Q being the charge of the particle with the potential energy, and V being the electric potential. Basically, the electric potential tells us how the point charge provides Q, the test charge, with potential energy. To help make sense of this, let's compare it to a gravitational potential energy. If you have a ball on a hill, it has a potential energy due to gravity that is equal to the mass times gravity times the height. And this g represents the acceleration due to gravity, which on Earth is 9.8 meters per second. The electric potential energy is a lot like that. It takes into account the test charge magnitude, like the mass of the ball, and the voltage, which we earlier learned was negative ED, and that can be compared to this GH. But rather than gravity, it's the effect of the electric field. Voltage is a scalar quantity, which means that unlike an electric field, it does not have a direction. Since it depends on the magnitude of a test charge and its distance from the point charge, it creates interesting patterns, which leads us back to equipotential lines. On equipotentials, the electric potential for a certain charge is the same anywhere that is the same radius from a charge. So if all of these radii are the same, sorry, this picture's getting crowded, then the voltage at all of these points will be the same. These equipotential lines are always perpendicular to the field lines. So even when there are multiple charges and things get more complicated, you can draw them as long as you have the field lines. Another key point to remember about equipotential lines is that no work is required to move a charge along an equipotential. Why is that? Well, if we check out the work equation, we see that work equals the negative change in potential energy. We saw earlier that PE equals Q times V, so this means that work equals negative Q times delta V. Since V does not change along equipotential lines, the delta V equals 0, which makes the work 0 as well. So the three main points to remember is that the voltage or electric potential does not change along the equipotential lines. The second point is that equipotential lines are always perpendicular to field lines. And the third point is that no work is done along equipotential lines. As long as you remember those 3 points, you'll be able to master equipotential lines and understand what they mean.